Swayam Prabha. Digital India. Educated India.
So, good afternoon and welcome to the class today. We were discussing this concept of subspace, and we will continue from that. And the idea is, let us consider the space R2, okay. Consider the space R2. What do I mean by R2? I mean each vector has two coordinates, okay, and means each vector has two elements, and we saw that in Rn you can have a maximum of n independent vectors. We saw this earlier, okay, and therefore the dimension of the space was n. So, here we can have a maximum of two independent vectors, therefore the dimension is 2. I mean, if you remember, we showed this for Rn, that a set of n plus 1 vectors was dependent, okay, because the number of unknowns is more than the number of equations, and you can always assign a non-zero value to one of the coefficients. That was the argument we made, and so if the number of vectors is more than the number of elements, it is dependent, okay. And we took one example to show that n would be independent, and because that is the maximum number which can be dependent, that is the dimension. That was the logic, okay. So, you can go back and refresh. So, I am saying here the dimension is 2, and for example, you can choose 1 0, 0 1. These are two independent vectors, or you can choose 1 1 and 2 3. These are two independent vectors, okay. And what is the meaning of this? That means that these two vectors, these two, let us call this u1 u2, or I am going to call this e1 e2, and this I am going to call u1 u2, okay. These two vectors e1 e2 or u1 u2 generate the space R2. Generate the space R2 means they are any vector in R2 can be written as the linear combination of these two vectors, okay. This means any vector in R2 can be written as a linear combination of E1 E2 or U1 U2, okay. So, basically that is what it is. Now, supposing I take two vectors. Now, suppose I take two vectors, let us say 2 3 and 4 6. these are also two vectors, but they are not independent, they are dependent on each other. One is the double of the other, okay. They are basically on the same line, the vector goes the same direction, okay. So, these are two dependent vectors. Why do I say these are dependent vectors? Because what was the way we found out? I look at sigma Ci ui equal to 0. I want to see if I can get a non-zero Ci, okay, and the answer is, of course, you can get a non-zero Ci. For example, if I take, what is it, 2, 3, 4, 6, right, 2, 3 and 4, 6, C2, C1 equals 0, I can choose C2 to be equal to 1 and C1 to be equal to minus 2. That will satisfy this, because this is double of this, okay. So, of course, C1 equal to C2 equal to 0 satisfies. This is, let us say, equation 1. But the question is, can there be a non-zero Ci? And the answer is yes. We can also have a non-zero combination. That is what we are looking for. If this is not possible, only this is possible, then I conclude that it is, if only this possible, I say it is independent, okay. So, I just said C2 equals 1, C1 equals minus 2, therefore, vectors are dependent. Now, supposing you take scalar multiples of this or vector additions of this, these starting with these two vectors, I just look at scalar multiples of these two vectors and vectors additions of these two vectors. Scalar multiples and vector additions of 2, 3 and 4, 6, okay, will all lie along a line, because this is 2, that is 3, so I have to draw like that, huh? This is 2, 3, this is the point 2, 3, you go like this, it is 4, 6 is here. So, now you just multiply it by scalar, I will get a vector along that line. If I add these two vectors, after multiplying by scalar, I will again get vectors along that line, okay. So, basically, this is 2, 3, this is the point, sorry, let me not draw a triangle and all that, this is the point 2, 3, that is the point 4, 6. So, I will only get vectors along the line, but is that R2? R2 means I should be able to get vectors in this plane, I should be able to get this vector, I should be able to get this vector, okay. So, these two vectors do not span R2, they have two coordinates, each of the vectors has two coordinates, 2, 3, whatever it is, but that does not mean they belong to R2, okay. So, basically, what I am saying is, this space generated by these two vectors is not R2, it is a subspace of R2. And what is the dimension of this subspace? Dimension of R2 is 2. Dimension of the subspace is 1, because there is only one independent vector. Okay. One, as we have only one independent vector. Okay. That is the reason the subspace. If the space, if there are two coordinates and they were independent, like in the first case 1 0 0 1, I will have two independent vectors, the space generated will have dimension 2, okay, and that will basically help me generate. So, you understand, I cannot generate this vector, I have this is also belonging to R2 because it has two coordinates, but can I get it by adding or doing scalar multiple of this? No, I can only get vectors along this line. So, this vector OA cannot be generated by 2 3 or 4 6. Okay, you can do scalar multiplication, you can add, you can do whatever you want, you can stand upside down, you won't get OA. Okay, so basically you are only along this line, and line has the dimension 1, so it's like a one dimensional subspace. Okay. So, the space generated by these two is not R2, because if it is R2, I need to have two independent vectors, okay, and it is not R1 because I have two coordinates. So, it is a subspace of R2 because it has two coordinates, it is a subspace of R2. That's something you have to think about and you have to understand. Okay. So, think about it. I want to talk about what is called the basis. So, the basis is a set of linearly independent vectors in the generating set of a space. Okay, so basis of a vector space is a set of linearly independent vectors in the generating set. Okay. So, dimension refers to the number of independent vectors. The vectors are forming the basis. Okay. So, in the earlier example, I had 1 0 0 1, okay, and that is the generating set for R2 because any vector. So, for example, 1 0 0 1 is a generating set for R2 because any vector in R2 can be written as a linear combination of these two. Okay. And I had one more example which I do not remember what I wrote, 1 1 2 3 I think is also a generating set of R2. Okay, both of these are generating sets. What is the meaning of generating set? This set of vectors generates all the vectors in R2. I can use these two to give me a vector in R2 with two coordinates. I will write it as a linear combination of these two. Okay. So, just I am explaining with R2 because it is easy for you to understand. Now, and these are basically independent, this is also independent. Okay. So, basically what have I said, the vector space is basis of a vector space, a set of linearly independent vectors of the generating set. So, this is set of linearly independent vectors, there is also a set of linear independent vectors. Both of these are candidates for basis. This can also be used as a basis, this can also be used as a basis. Okay. So, both 0 1 1 0 and 1 1 2 3 can be used as a basis. So, when I say basis for R2, okay. So, what does this mean? What do I mean by basis? If I take any arbitrary vector, I can write it as a linear combination of the basis. I can write it, so basis is just a set of vectors and I can take any vector and write it as a linear combination. Okay, that is what I mean by basis. So, let me just to make things clear, if we take an arbitrary vector let us say V, okay, we can write it as a linear combination of the basis vectors, and let us say the basis vectors are u1, u2. Okay. So, basically what this means is V is sigma Ci ui. In this case, I am just taking 2 dimensions, so I put 2, but it can be n. So, this is basically what I mean. Ui is a basis, and I told you basis is basically a set of linearly independent vectors. So, in Rn, a set of n linearly independent vectors will form a basis. Okay. So, you can take any set of n independent vectors, okay, and that is the basis, which means any vector, any other vector can be written as a linear combination of these bases, these vectors. Okay. For example, in R2 this is a basis, in R2 this is a basis because two independent vectors. But if I have 1 0 and 4 0, that is not a basis because they are not independent, they are dependent. Okay. I already know that in Rn I can have a maximum of n independent vectors. Okay. So, if I have n independent vectors, that will form a basis. So, when I write an equation of this kind, V equals sigma Ci ui, I equals 1 through n, okay, I am just generalizing it to n. My question is this representation unique? Okay. Now, when I write like this, what is given to me and what do I have to find out? What is given to me is the basis, what is given to me is also the unknown vector v. I need to find out these coefficients Ci. Okay. So, my question is, are these coefficients Ci unique? Can there be multiple solutions to the Ci? Okay. So, this is the basis which is known to me. This is the unknown vector. Well, if I say unknown, maybe I do not know it, but I know this, okay. But I am trying to represent it in the form of these bases. So, it is a known unknown vector, okay. Okay, so also is known to me, and this is what we have to figure out, okay. So, let me write, I will put this un in a bracket, okay. So, basically I am trying to have in R3 you give me 3 vectors, that is the basis, I am giving a 4th vector which is known, but I am writing it in terms of these 3, okay. Is the Ci unique? Okay. Supposing, so I think the proof is very simple, just two lines, you will prove by contradiction. So, assume it is not unique. If it is not unique, what does it mean? There is another set of coefficients Bi which can satisfy this, okay. So, proof is by contradiction, okay. Assume it is not unique. Then what does it mean? I can have V equals sigma Bi ui for I equals 1 through n. Some other coefficients exist, okay. What I am going to do is I am going to subtract these 2 equations, okay. Subtract these 2. Now, what do I get? 0 equals sigma Bi minus Ci ui, I equals 1 through n. All I have done is subtracted, okay. V and V, subtract, you get 0. But now remember ui is a basis, which means they are linearly independent, okay. That was the definition of basis, they are linearly independent, and if there is a linearly independent set, I know that this can be satisfied only if these coefficients are 0, okay. Since ui is a basis, it is linearly independent, the above equation will be satisfied only by the trivial relation which is Bi equals Ci. All the coefficients have to be 0. So, basically I am saying that the representation is unique, okay. So, given a particular basis, there is only one way to represent an unknown vector, okay, an arbitrary vector, sorry, and you can have more than one set of vectors as basis, not that basis is unique. That is something which you have to understand. I gave that example 1 0 0 1 and any 2 independent vectors you can take. So, basically when we are trying to solve problems tomorrow, we will solve equations of the form Ax equals b, Au equals b. We are trying to find this unknown vector u which satisfies that equation. Okay. So, we will be writing that in terms of a basis, that is where this is all going to. So, all these concepts are going to be used somewhere tomorrow when we solve these equations, because I do not want to just say something and go on. So, these whatever concepts I am discussing now are going to be used for the solution of problems tomorrow. Okay. So, they are not completely abstract and useless. So, do not think they are useless. They are of course useful, because in the exam I am going to ask you. Okay. So, in solving problems, we will represent vectors in terms of a basis set. Okay. We will basis set, I am going to call this basis set ui. So, supposing I have, let us consider 1 1 1, 1 2 1, I am hoping that these are independent. I think they are. Okay. I just added something and I changed the last number, so it has to be. So, basically these are 3 vectors which are independent. Okay. And they all have 3 coordinates. Okay. So, they are basically these 3 vectors. So, let me call this u1, u2, u3. Okay. And you can check that u1, u2, u3 are independent. Okay, first I am going to ask you, are u1, u2, u3 independent? First question. So, how do you check that? You have to find this thing. Let us go back a little bit and do things a bit more slowly. So, I have to look at sigma Ci ui, okay, and which means I will write C1 multiplied by 1 1 1 plus C2 multiplied by 1 2 1 plus C3 multiplied by 2 3 4 equals 0. Now, what do? You will just write this as, and we are trying to find C1, C2, C3. Okay. So, C1 plus C2 plus 2 C3 equals 0, C1 plus 2 C2 plus 3 C3 equals 0, and C1 plus C2 plus 4 C3 equals 0. My job is to find the CIs and to see if I can have a non-zero CI. If I can get a non-zero CI which satisfies these equations, even if one CI is non-zero, it is dependent. Okay. So, even if one CI is non-zero, it is dependent. If only Ci equal to 0, that is C1 equal to C2 equal to C3 equal to 0 satisfies these equations, it is independent. Okay. I am not going to do this, but I want you to sit at home and figure out that you have to take my word for it today, that the only solution that I can have is C1 equal to C2 equal to C3 equal to 0. Okay. You can't, but how will you do it? You just have to eliminate, no? I mean, you will eliminate C1 from these two, subtract, get an equation C2, C3, eliminate C1 from these two, get equation C2, C3, then eliminate C2 or C3, and you will see that only 0 satisfies. Okay. So, that is what you have to do. So, what have I established? That these are independent and there are three vectors, and therefore, and these are 3 elements, therefore, these can be used as a basis for R3. I can take any vector and I can write it. Okay. So, basically I am saying these 3 vectors can be used as a basis because they are independent. If I give you 3 vectors, can I use it as a basis? Only if they are independent. Can I use it as a basis for R3? If all of them are independent, I can use it as a basis for R3. But if 2 are independent, then I will can use it as a basis for a subspace of R3. I can't, because I have only 2 independent vectors. Okay. So, now if I have I should not say unknown, maybe arbitrary vector V, which I will put some ridiculous numbers 13, 21, 9, something like this. Okay, so, some arbitrary vector is there. I want to express it as a linear combination of my bases, okay, because that is the idea. Any vector in R3 can be written as a linear combination of the bases. So, now I am going to write 13, let me write it like this. On the right hand side I want to write 13, 21 and 9, C1 multiplied by 1, 1, 1 plus C2 multiplied by 1, 2, 1 plus C3 multiplied by that crazy thing which is 2, 3, 4. Okay. So, now because the right hand side is not 0, I will get a non-zero value for C1, C2, C3 are 3 equations and 3 unknowns. Okay. You can solve these 3 equations and 3 unknowns and you can find C1, C2, C3 using anything that you want, any method that you can think of. So, we have unknowns and can solve to get a non-zero C1, C2, C3. So, I am interested in these coefficients because I want to represent my arbitrary vector in terms of this set, this basis set. I want to find out my C1, C2, C3. These are the coefficients of the basis. So, basically if I have to find these coefficients and supposing you are dealing with a large dimensional system where n is maybe 100, 1000, 5000, then you have to solve a system of large equations to find these coefficients. Okay. If it is 2 equations you can do it, 3 equations you can do it, maybe 10 equations you can do it, but as you keep increasing the number of variables, okay, as the dimension of the space increases, Rn increases, I mean you have to solve that many more equations. So, is there a more efficient way of doing it? A more efficient way comes when the basis it is not just independent, but is also orthogonal. Okay. Right now, I gave you an example of when the basis is only independent. So, when it's only independent, this is what you have to do. You have to solve a system of linear equations to solve, to find the coefficients. Okay. But if it is also orthogonal, orthogonal is also independent. So, if on top of being independent is also orthogonal, then is the more efficient way of calculating these coefficients Ci. Okay, that is what I want to show. So, if the basis is only independent, or rather let me just say independent, then we have to solve a system of n equations to find the Ci's. But in addition to being independent, it is also orthogonal. But if the basis is also orthogonal, then Ci's can be found easily without having to solve n equations in n unknowns. Okay. Like what I did. So, now let me call this vector some b. Okay. So, I am saying now b is written as sigma Ci ui, where the ui are orthogonal. Okay. So, again I illustrated for just a simple 3-dimensional case, 3 vectors, 3 elements, and then we will see. So, B is written as C1 U1 plus C2 U2 plus C3 U3. Okay. And remember, U1, U2, U3 are orthogonal. That means U1 is perpendicular to U2, U1 is perpendicular to U3, U2 is perpendicular to U3. Okay. What does that mean? Inner product of U1 with U2 equals inner product of U2 with U3 equals inner product of U1 with U3 equals 0, because they are orthogonal. That is what I mean by orthogonality. Okay, dot product is 0, inner product is 0. So, what I am going to do now is I am going to take the inner product on both sides with U1. Okay. If I take the inner product of both sides with U1, what do I get? Yeah, I am taking I will do inner product of B with U1. Okay. This is inner product of C1 U1 plus C2 U2 plus C3 U3 with U1, and from the axioms of inner product, this can be written as inner product C1 U1 with U1 plus inner product of C2 U2 with U1 plus inner product of C3 U3 with U1. Okay, because that is what we said from the axioms. If you go back to the axioms, this has to be satisfied. So, basically what I am saying is, I am just taking inner product is just like taking the projection. So, I am doing inner product on both sides with U1, okay. And if the scalar multiple, because now the scalar multiple is multiplying the first vector, when I take it out, it is going to become the complex conjugate if it is complex. If it is real, it does not matter, it will be C1 only, okay. So, this is going to be C1 bar U1 plus C2 bar inner product of U2 with U1 plus C3 bar inner product of U3 with U1, okay. Now, these are all coming from the axioms which an inner product has to satisfy, which we saw earlier. So, I mean yeah. So, now these two are orthogonal, so that goes to 0. These two are orthogonal, that goes to 0. U1 is not orthogonal to itself, okay. So, this will be present. So, basically all I am saying is C1 bar, that coefficient, inner product of B with U1 divided by inner product of U1 with U1, okay. So, all you have, and finding the inner product is straightforward, right, because it is just sigma ui vi, the way we find the dot product of two vectors, that is how we defined it. So, point I am trying to make here is, for any arbitrary Ci will be inner product of B with ui divided by inner product of ui with ui. What this basically means is, if my basis set is orthogonal, if the vectors are all perpendicular to each other, then I can find the coefficients very in a straightforward manner, okay, by just taking the inner product. And that is what you have been doing. I mean, so far whatever you have been doing, when you are writing a 3-dimensional vector, you write it in terms of I, j, k, unit vector in the x direction, y direction and z direction, they are perpendicular. So, give you any arbitrary vector, you can write it in terms of the components. So, let me try to tell you that whatever I am talked about just now is something you are already familiar with, okay. So, for example, when, so if the basis is orthogonal, we can find the coefficients elegantly. I mean, without having to solve. So, even if your vector has a dimension of 1000, you can just do this inner product 1000 times. You do not have to sit and do Gauss Jordan, Gauss Seidel and all that, okay. So, this is a much better way. So, in physics, you write vector V as 3i plus, let us say, 4j plus 18k, that is the maximum number I can think of today, okay, 18k. What is I? I is unit vector in x direction. So, I will say x is my first direction. So, 3 times 1 0 0, 4 times 0 1 0, 18 times 0 0 1, and V will be 3 4 18. So, whatever you have done so far, writing an arbitrary vector in terms of I j k, is, so my vector in my mathematical language, my not in the geometric but algebraic representation is 3, 4, 18. So, this is my arbitrary vector. These are my u1, u2, u3, which are orthogonal to each other, perpendicular. Take the inner product, you get 0. And because they are orthogonal, I can find these coefficients in a very straightforward manner. If these have not been orthogonal, then I have to solve a system of 3 equations and 3 unknowns. Okay. So, point I am trying to make here is, this is, I mean, you are used to unit vector in x direction. Instead of saying unit vector in x direction, I am algebraically I am representing it as 1, 0, 0. Unit vector in the y direction 0, 1, 0. Unit vector in the z direction 0, 0, 1. So, that is because tomorrow I mean I have to go beyond 3 dimensions, 4 dimensions, okay, 20 dimensions. So, for visualization it is easier, okay. So, this is basically, this is the unit vector in x, in y, in z direction. But rather than talk only x, y, z, which you have been comfortable with, I am talking about any direction. I do not want to restrict myself to only 3 dimensions geometrically. I want to go to higher dimensions, 50 dimensions, 100 dimensions, because my vector may have, I may be solving some distillation column where lots of variables are there. I want to visualize that as a vector, okay. So, then I do not have this x, y, z concept. So, I right on the first day I mentioned geometric representation, algebraic representation, okay. What you have seen here is what I would call the geometric representation, but I am shifting towards algebraic. If I write in terms I, j, k, x, y, z, it is geometric, but when I write it in terms of 1, 0, 0, that is algebraic, okay. So, this is the algebraic representation, and I will call this geometric because I, j, k, I think of x, y, z, okay. This is geometric. So, I am just going back to the very first thing I spoke about, algebraic and geometric representation. So, bottom line is we would like the basis set to be orthogonal, okay, and then it is easy for us to do a representation of arbitrary vectors. So, given a particular set of vectors which are not orthogonal, I give you, let us say, 2 vectors which are independent but not orthogonal. Can I construct 2 vectors which are orthogonal, okay? The answer is yes. We will see how to do that tomorrow. Thank you.